All right. Morning, everyone. First order of business. Did you guys get the email about the assignment? Yep. No? Okay. Three out of 4 is not bad. Yeah, so basically I finally got the assignment sorted for you guys. So if you go to Learn on week 4, you'll see there's the assignment there, which should allow you to upload your submissions and whatnot. But basically the idea is trying to do something which involves a bit of processing, a bit of 3D graphics, and a bit of AR, since that's what we do at the lab. So, starting from we have a warehouse and we want to design some sort of wearable computing, augmented reality interface, whatever, to help people find stuff in there. So in order to do that, we're going to start by creating a warehouse simulator. So there's some code on the site. If you look at the example code here, download that, which basically does this. So I put through this together the other day. It's just basically the move eye example, but modified a wee bit. So now instead of just drawing one box, it draws like a 10 by 10 array of boxes, and it also allows you to move the camera around using the keyboard and mouse. So we just run this quickly so you can have a look. So we can, as we move the mouse from side to side, you can see it turns around, and then using the AWSD keys you can traverse through. Yeah, so there's obviously no collision detection or anything like that because I couldn't be bothered spending that much time on it. But it gives you the idea that you could imagine that this is the sort of start of your warehouse. So you guys are welcome to start with that code. We'll just have a little look at it. There's nothing too surprising. So position X and position Z are the position of the cameras in the X and Z plane. So Y is obviously vertical and X and Z are on the ground. Rot angle is the rotation angle of the camera, so it only moves from side to side at the moment. If you want to make it so you can look up and down and stuff, go right ahead. Cheers. Then there's some things for some booleans for move left, move right, move forward, move backwards, which basically when you push the key down, those become true. When you let go, they become false, because otherwise, basically it just makes the movement smoother. Setup, nothing surprising there. We set the size and we set the fill color. Turn it in the drawer, we turn on the lights, turn on the background, and there's a little bit of code in here which basically handles the camera movement and orientation. So unless you want to make it so you can rotate in multiple directions or fly through space or whatever, you probably don't need to worry too much about this. But basically there's begin camera and end camera, which allows us to set the camera parameters with a bit more a bit finer control than move eye or one of these other things, which is why I chose to do it this way. I tried to get it working with move eye, but it was a pain in the ass. Reset matrix is basically just sets the matrix to 0. Then we have 2 functions: update angle and update position. So update angle just calculates the angle using the position of the mouse on the screen. So this is a little bit different from what we've seen before with mouse X and mouse Y, because mouse X and mouse Y are actually clipped to the window of the processing window, so it only measures. This is 0, 0 in mouse X. This is window or screen X for mouse X. So if you do mouse X, you actually rotate the camera this far, which is a bit of a pain. Being able to move it the whole window, I think, just makes it a little bit easier to navigate, but it's neither here nor there really. But yeah, so basically it gets the mouse position and uses that to calculate the orientation. Then we have update position, which is down here, and basically if we're pressing the forward button, we calculate the Z and X by the cosine, positive cosine and the negative sign, and move back is blah 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 blah, so on and so forth. And 10 is basically the distance measurement, so if you want to make it move faster, increase that number. If you want to make it move slower, decrease that number. But again, you probably don't really, well, for the assignment anyway, you don't have to modify update position, update angle, or any of the camera code if you don't want to. Certainly there's no marks for doing it. And then, so we update angle, update position, rotate the camera, and translate the camera. Now this is where you guys are going to be doing your work. So you'll see here, no stroke obviously turns off the outlines. But yeah, we loop through a 10 by 10 array, so 10 in one dimension, 10 in the other dimension, translate to that position, and draw a box. And then this part here is just to draw those lines. So this is actually directly copied off the directly copied off the MoveI example. So if we copy that out, it's actually potentially even more warehouse-like because the boxes don't have lines jutting out of them. But it was just to give you guys an idea of which direction everything's facing. So yeah, your assignment basically is to take the example that you've been provided and modify it to look more like a warehouse. So it doesn't have to look like this, but you should at least maybe throw some textures on it, and you can put in a plane for the floor and whatever else you want to do. The software demo is marked out of 30, and there'll be like 5 points that'll be for how exciting, interesting your warehouse is. So, at the very least, you should maybe throw some textures on the boxes and make it look a little bit prettier, but you can go all out and make the next Far Cry if you really want. Probably don't have time for that, though. So that's part one. Part two is to then create like an augmented reality interface to help people find a specific object in the warehouse. So with the example one, if I said to you guys, find the box at position 8 by 9, assuming it's 10 by 10 grid, you'd have, for one thing, we don't actually know which is the front, which is the back, which is the side, and so on here. And even if you did, you'd still have to sort of count your rows along and find it, and it would be quite time consuming. So what we want to do is create a little augmented reality interface to do it for us. I threw together a couple of very basic examples, so I'm not going to give you guys the code for this because this is what you're going to be doing. But so this is the default one, and this is one possible example you might want to choose. So I've just picked one of the boxes at random, and where are we now? So if we look, you can just see there is one box which is colored purple. So it's probably maybe not the easiest way, but it makes it a little bit easier than just having all grey boxes and having to count them out. So that could be an example of one interface. I made another one here which makes it slightly easier again. So now it becomes kind of obvious which box we're looking at. There's one in here, and it's obviously that box, which is shrinking and growing, is the one we want to select. So, there's sort of ideas, play some video games, watch some movies, have a look at these sci-fi interfaces where people are tracking stuff. You might want a little radar in the corner which shows where boxes are relative to you. You can do arrows pointing down from the ceiling saying, hey, here's the box. It's completely up to you guys. That's the bulk of the assignment really, is to come up with that. So yeah, modify the example so it's not just plain boxes, make it a bit more visually interesting. There'll be a few marks for how cool it is at the end, but only a few. So if all you manage to do is throw some textures on it, you'll still get most of the marks. Then on paper, sketch out some ideas for what you might like to do. So you might like to have, as I said, a little radar in the corner showing where things are. You might want to do other things. And then once you've picked some things you think which will work quite well, implement the interface like those couple of examples I saw there. So for example, those two examples, I think they're about 3 or 4 lines of code per example. So, theoretically you can get away with some pretty minimal stuff to get some effects if you guys want, but, it's up to you how far you choose to take it. So the deliverables, I'll want your source code, and obviously if you're using textures or whatever, zip it all up and just dump the entire directory with the source code file and the textures and whatever else. A one-page document of the interface you've designed, so basically saying I chose these features, here's why I chose them, here's how they work, here's why I think they would help someone. If you've done any sketches or anything you can do, like include them as an appendix. And then at the end, or when you've submitted it, so the due date is 19th at 11:55 p.m. So basically midnight. Because if you say 12 p.m., people are never sure if you meant like the Wednesday or the Tuesday. So it's 11:55 p.m. on Tuesday. So 2 weeks from yesterday, basically. And the drop dead date's a week after that, but you'll lose marks like 1% a day or something for every day after the due date you are. And yeah, so at the end you'll basically give a live demo of your program with 3 minutes maximum. But basically you just run through and sort of show what I've shown today. So you just be like, so these are the features I decided to include. So I've got the box which shrinks and grows because it makes it really easy from a faraway distance what's going on. what you'd be graded on. So the demo, which is what you send to me, 30 marks, about 5 will probably be for coolness. Your source code style, so you should be using things like writing. If you're doing one thing over and over again, you should write it in a function. You shouldn't just copy and paste the code 100 times. You should call a function 100 times. Using push and pop matrix rather than translating one way and then translating back to get back to where you are. These sorts of things we've talked about in class. 15 points for the document that you'll provide, 20 points for the presentation, and 20 points for the quality, which will just be sort of overall how good a job you've done creating an interface. Yeah. Anyone have any questions? No? So I tried to pick something which was, achievable, but would be kind of fun as well. I've done the camera movement, which was probably the hard part. So I spent about 45 minutes getting that working, so I thought I'd save you guys a bit of time. All right, anyway, so that's there. You've got a couple of weeks. Feel free, you have to submit your own assignments, and they should be your own work, but you're welcome to chat amongst each other. If someone's having problems, you can ask for help from each other or from me or one of the other masters guys. They've all done processing and stuff as well. So, yeah, feel free to sort of talk things through, but the work you should submit should be your own work. So I don't want 4 people who've just made a box which shrinks and grows. All right, so we'll pick up from where we left off yesterday. So I've got some Arduinos here. I currently have 3. There should be another 2 coming today. In fact, they may even already be here, if not by tomorrow. So one of you might just have to hold out a little bit longer to get them. So these, we have 2 different kits. They're both the SparkFun Inventors kits. This is the older style one, and this is the newer style one. They pretty much have exactly the same stuff in them anyway, so don't worry about which one you get. They have been used by the last group of students, so you might find some of them have stuff which other ones don't. Some of them might be missing stuff. This one's a little bit light on the components, but I've also ordered a beginner's pack, or like a resources pack, which is basically all the bits and pieces apart from the Arduino, so like the wires, the sensors, all that sort of stuff. So if you're missing anything, I'll make that available for you guys to rummage through, or otherwise if you're looking for something and your kit doesn't have it, feel free to steal it off someone else, or ask the master's students if it's floating around the lab, or you can see if one of the guys in the hardware lab can have a look at it for you, or if you need a specialized component, let us know and we can order it for you. So, unfortunately, it gets kind of expensive ordering new kits every time, and people borrow stuff and then forget to put it back. But, you'll be able to get all the stuff you need. It might just require a little bit of chasing to try and get it. Anyway, prototyping hardware. So we looked at all the stuff on Monday. So we talked about all the bug labs and this long tail of consumer electronics where there's a big section for new markets which aren't going to sell. You're not going to sell hundreds of millions of devices, but if you can do something for cheap and easy enough, there's plenty of stuff out there which people want. Then we started talking about the Arduino specifically, various Arduino components, how you can buy shields which fit on top of them, devices and sensors which can plug into them, and phone hardware. So just while we're there, so there's a bunch of websites you can look at for sort of inspiration on devices and stuff. So one's Deal Extreme. I don't know if you guys have heard about this. It's like this huge big online electronics retailer out of China. They do free international shipping, and they've got everything you could possibly ever want on there. But they also do a ton of Arduino stuff for dirt cheap, really. Could use a bit more sugar. Yeah, so it's running a little bit slow today, unfortunately. But so yeah, things, relay boards for controlling. So it's 5-volt relay. So if you need to switch something on and off, potentiometers, proto boards, sensor shields, all this sort of stuff. You look at these prices, it's like $4, and that's free shipping as well. So, that's $4 US, but that's probably what, $6 or $7 New Zealand, free shipping. So, if you need stuff, have a look on Deal Extreme is a good place to go. if you can't be bothered waiting, because it does take, you know, a couple of weeks to a month for the shipping to arrive from Hong Kong. There's Nice Gear, which is where I've got all of your guys' Arduino stuff from. So all the SparkFun kits and stuff come from Nice Gear, and they've got various, so you've got your Arduino boards, you've got some shields, and they sell a bunch of other generic electronics gear as well that you can just buy and stuff into. Or rather plug into your Arduino to get stuff going, so yeah, lots of stuff. Anyway, so yeah, there's a bunch of websites, have a look around them and get some inspiration, particularly Deal Extreme. It's a site you could easily lose a day in just looking through all this junk you never realized you actually wanted or needed, and you probably still don't, but it's so cheap you can't help yourself. Right, so we finished looking at all the Arduino stuff, and then we were going to look at the Arduino IDE, or the Arduino software side of things. So first of all, might just switch those lights back on. So this is the Arduino that you guys get. Well, there's actually, depending on which board you get, you'll get a SparkFun red board or an Arduino Uno. Basically, the difference between them is this one is red, this one is blue. They actually have pretty much exactly the same stuff, I think. There's a different USB connector and a few other different things, but pretty sure the app-mailed chip they're using on them is exactly the same. So, you know, you're not going to be like limited by the amount of processing power depending on which one you pick. Really, the main difference is one's painted red, the other's painted blue. So if your kit doesn't have a USB cable, and you know some of them are the old style USB printer cables and some of the more modern USB minis, go talk to Greg, or if he's not here, I think he might actually be on holiday at the moment, talk to me and I can get you a cable. So when we plug it in, you guys all using Windows or? Okay, well, that makes it easy. Yeah, so when you plug it in, you know, you get the little thing and it might install some driver software. The driver software should just be picked up automatically by Windows, because basically what happens is it enumerates as a USB serial port. So it's using a default Windows driver. If it doesn't work, have a look on the Arduino website, and if you can't get it working, let me know, and maybe the board's stuffed. But yeah, so basically if you go into right-click on computer, go Properties, and then go to Device Manager, hopefully you should see something which says USB serial port on here, and keep an eye, or just make a note of what COM port it attaches to, because you need to know that to program it. For this computer, for some reason, it has like a dozen serial of Bluetooth ones, which was actually causing the Arduino software to basically crash. So I've disabled all of that. So if you're having problems with the Arduino software, check how many serial ports you have, and if you're not using them, just disable them. You can always just right-click and go disable. And then if you want to re-enable them, right-click and go enable. It won't do any harm. It'll just mean that you can't use them. Right, so Arduino. So the Arduino software should look quite familiar. That's because it's basically processing. Uses the exact same IDE with a few minor tweaks. So what we want to do first when we load it up is click on Tools. Depending on how many COM ports you have, when I first did this, it took about 10 minutes for it to pop up this window, because it tries to enumerate every COM port, and it's an absolute nightmare. So another good reason for disabling all your COM ports if you're not using them. But you want to go down to serial port and make sure you're on the right serial port. So you see USB serial port COM8. I want to make sure COM8 is selected. And then for board, all the ones which come in these SparkFun kits are the Arduino Uno. So you just click on that and we're ready to go. So Arduino is based on C programming. It's pretty, well, it's not, there's nothing that complicated. It's like a very stripped down version of C. So it's C in the same way that like Java is very similar format for the processing stuff you guys have been doing. So if you can write processing code, you can write Arduino code. It's, you know, such a small subset language that, you know, there's nothing there which is going to surprise you. There's no weird C++ functions, templates, any of that sort of stuff. Yeah, so it all looks pretty much the same as the processing thing. All you need to know in the tools is basically board and serial port and maybe serial monitor, which we might look at in a minute. Sketch, so we have import library like we did with processing, except now they're all like hardware stuff, so stuff for communicating with an EPROM, communicating the firm ATA, which we'll look at later in class, liquid crystal displays, servo motors, etc., etc., etc. A bunch of various edit stuff. Oop. And examples, fortunately, come as well, standard, in a slightly different way. It's all like based off menus rather than pop-up window. But yeah, so if we go into examples and basics and bare minimum, this is what your Arduino sketch will look like. Obviously, it doesn't have a draw method because there's nothing to draw on because we're running it on hardware. We basically have two functions, one which is setup, which happens when we first turn our Arduino on, we first plug it in, and one which is loop, which runs as fast as the Arduino can possibly process it. So this code gets run once, and then code just runs and runs and runs. You can do all the same things you can do with processing, so you can create a new function, and then you can call your new function if you so want. Let me just check this. I think might need to. Don't think it has forward referencing. Maybe it will work. Yeah, so obviously nothing is actually happening in here, but loop will call new function now, so you can put code in here and split it up like you would with processing. So, yeah. So the Arduino IDE is open source. It's processing, so it has to be. It's cross-platform, so Windows, Mac OS X, Linux, doesn't really matter for you guys. And it's got a simple UI, so it's really easy to use. It's got lots of built-in examples and some pre-installed commonly used libraries for controlling various bits and pieces of hardware. And if we go to the site as well, there's like all your typical stuff that you come to expect from these sort of open source projects. So it's got, obviously you can buy it. You can download. If you need to download the IDE, you just go to the website and hit download, and then grab whatever copy you want. So 105 is the stable one, but you can do 1.5.7 if you need to do an Arduino Yun, I'm not sure how that's pronounced, or Arduino Due, which we won't be using either of those boards, but I think the Arduino Yun actually runs Linux rather than, the standard stuff. But if you want to do that later on, by all means, but 1.0.5 will do for the meantime. Then there's, okay, everything's gone, oh, there we go. So you can buy products off them. So if you go into learning again, there's plenty of information there about the environment, various libraries, and there's information about all the examples on there as well. So this is quite nice in that you can go to an example and it actually has a tutorial. Obviously this is a bit more, Arduinos are a bit more complicated than processing because you actually need to plug hardware into them, but all the examples will show you a picture of what it looks like when you have everything plugged in. It also has the electronic schematics, and then it'll have the code, and it like references all the functions that you're going to need to use, as well as related examples and stuff. So yeah, definitely have a look at that. And then there's all the reference material as well, same as processing, so all the functions you might need to call, and support. There's frequently asked questions forum and all that sort of stuff. So yeah, let's close that down and have a look at our very first Arduino. What's going on here? Our very first Arduino sketch. So you can see at the moment this is powered on and it's doing absolutely nothing. So what we'll do is we will load up what's known as the blink sketch. So there's sort of a few things on the Arduino board which are sort of special. So you've got all your digital I/O pins down here, you've got your analog I/O pins down here, you've got your power pins here, and you can plug anything into any of these, obviously. There's a few special things like this light down here which has 13 next to it, and I think on these ones it says L. So you can see there's a little SMD LED on there. And on both of these boards, even though this one's labelled L and this one's labelled 13, they're both actually internally connected to pin 13. So if I plug something into pin 13 and do something on it, it'll also happen on that light there. So let's have a look at this code. So we create an integer and we define it, integer called LED, we'll define it as 13. So that's basically going to be the pin we're working on, so pin 13, which also happens to be connected to that little LED. So we have this pin mode function. So pin mode basically defines what sort of mode we're going to use the pin for. We're going to use it for output, so we're going to be outputting 0 volts to 5 volts on it, or is it going to be input, so we're going to read either 0 volts or 5 volts from it. So we basically say pin mode LED, so we're setting this is equivalent to pin mode 13 is output, so we're saying, okay, set up pin 13 to be an output so I can put voltage on it. And then in our loop function, we write to LED, so pin 13 high, which is 5 volts. So we don't actually specify what voltage we're writing with these digital writes. We just say high, which is 5, or low, which is 0. So we write high first, and then we delay 1000, so this is milliseconds, so that's wait 1 second. And then we write low, so we set it to 0 volts, and then we wait 1 second. So now if we upload this, so it'll compile our sketch and then I'll upload it to the board. And now you can see pin 13 will turn on for a second and then off for a second. Super exciting. So if I grab some bits and pieces from here. So we'll grab another LED. And a couple of wires and 330 ohm resistor. So where are we? Pin 13. That way. Now hopefully, assuming I've plugged everything in the right place, then to ground. There we go. So now they're flashing in sync, because obviously, as I said, pin 13 is connected to that LED. So if I connect an LED into pin 13 as well, they'll both light up at the same time. So let's make this marginally more exciting, very marginally. Grab another couple of wires. Let's do pin 12 this time. Ground, and you see, so I've plugged another light in, but nothing's happening because it's plugged into pin 12 now, and I haven't actually told pin 12 to do anything, so it's just going to sit there and do nothing. So let's modify our code a little bit. So we'll say, okay, we actually want pin 12 to be output as well, and 12 high, whoops. 12 low, and let's cut this time down a wee bit. Right, so now I've basically set pin 13 and pin 12 to be output, and I've said, okay, when pin 13 is high, pin 12 should be low, and vice versa. So now I have like flashing yellow and red lights like a train crossing or something. I don't know. It's not particularly exciting again, but you know, before Arduinos and stuff, this was actually quite hard to do. I remember doing stuff like this in high school with like flip-flops and 555 timers and stuff, and it would take a lot longer than that. Right, so I'll just give you guys a bit of a rundown on what's going on here. So on the breadboard, we have rows of things we can plug into, obviously. So down here we have typically what's done as positive and negative strips. So all of these things are connected vertically. So let's see if I can get it. So this pin here is connected to this pin here, is connected to this pin here, is connected to this. So all of these running up here are connected, and on the negative, all of these connected to here are negative. So you can see at the moment I've got both of these plugged into the ground or there's 2 ground ports on the Arduino board. I've got them both plugged into there. But what I could just as easily do is plug them into these are commonly, these things known as rails, plug them both into the same rail, and then just plug that rail in. So now, you could sort of see if I wanted to add another LED and I've used up my 2 ground ports, I can't add another LED because I've got no more ground ports. So what I can do instead is just hook one of the ground ports to the rail and then just hook everything else to the rail. So now I've got all of these ports to go. So yeah, typically the negative one is connected to ground and the positive one you might connect to 5 volts or something. You don't obviously have to use them for anything at all if you don't want to. For the parts in the middle connect in the opposite direction. My fingers are too fat. So in the rails, these all connect vertically like that, but there's no connection horizontally, so this one doesn't connect to this one. Whereas on the breadboarding surface, it goes the other way. So all of these are connected in a straight line, but they're only connected to the ones to the side of them. So you see we've got this sort of ridge running down the middle that actually splits them. So all of these ones are connected and all of these ones are connected, but these ones are not connected to these ones. So if you ever want to connect it up, if you actually look at how I've connected it, it's basically this wire here connects to one leg of the LED and then that one goes into the next slot along this way. So because if we put them on the same slot, it'll basically be a short circuit. So you want to connect all your things down the breadboard like that. Yeah. Anyone have any questions? If you follow through the examples, it'll show you how to build the stuff on the breadboards anyway, but sort of gives you a basic example. Regarding like things like the orientation of the LEDs and stuff like that, we're going to look at that a little bit later anyway, because obviously there's LEDs. If I turn one of these ones around, nothing's going to happen because LEDs have a polarity, so they only work one way in the circuit. Right. Anyone have any questions?
No? Is the space between the 2 points in the resistor intentional? Did you just sort of...
No, that's just where the leg's bent to. Okay, yeah. So I mean, no, they could have been like one here and then one on the next one. It could have been one here and over here. Just as long as they're not sitting across the board, it's fine. It's just the way the resistor's leg's bent. They cross about 4 or 5 points. All right, so let's get back into this. So Arduino software, we've looked at this. So installing the IDE, again, it's just like processing. You just download a zip file and unzip it. So yeah, we want 105, and well, there's a Windows installer or a zip file that you can just unzip, and obviously one's for Mac OS and Linux and everything else. And then you just end up with something like this. So you have your Arduino exe file, and there's some drivers in case your board doesn't recognize immediately. It's got a folder with some drivers in it. You can try. It's got all the examples, and then it's got some other stuff, which were like stuff for basically compiling it and linking it. And because the Arduino IDE is written in Java, obviously it has all the Java stuff as well. And then it's actually got some reference information in here as well. So these are the HTML reference files actually come with the Arduino IDE, so you don't actually need to be connected to the internet, but how often does that happen these days? Yeah. So programming in Arduino. So, that's one thing. So yeah, I've uploaded my code, which is known as a sketch, to the Arduino. And once it's uploaded, it stays on there. So if I unplug that now and then plug this back in, it'll boot up for a second and then it'll go back to running the same code that it ran before. So once you've programmed it once, it'll stay programmed until you sort of, change the program. And, it doesn't even have to be plugged into USB. So it has a DC jack. You could plug it into a 9-volt battery. In fact, I did see a 9-volt battery in one of these ones. Yeah, well, that's not particularly useful. Let's see if I can do this. There we go. So now it's running off battery, so it's not even plugged into the computer, and I'll continue running the sketch. So yeah, I guess that's another little secret I probably should have mentioned. So you can plug, obviously, 9-volt batteries or power supplies or whatever into that. This power thing running over here, you can use it to either supply power to the board, so the board over here, but it also works the other way around as well. So if I plug my battery into 5 volts and ground on here, it will power the Arduino as well. So yeah, now we have something I can take that out and stick that wherever I want, because it's just running off battery power, or you can run off solar or whatever else. But it'll continue running the same sketch indefinitely until you reprogram it, basically. So yeah, we power on our Arduino, it resets itself. P13 blinks fast, that's just while it's booting up, and P13 is this little light here, and it's the L or loading light on this one. So you'll notice when I plug this in, both this light here and the yellow light will flash quite quickly just while it boots. And then once it's finished, it'll just continue on loading the program. So don't plug into anything into pin 13, which you don't want like powering on and off quickly when the Arduino starts. Use one of the other ports. In fact, usually you start at 1, obviously pin 13 is the highest pin, so, or at least on these boards it's the highest pin number, so you usually don't use it unless you're running out of them. But yeah, pin 13 blinks fast, and then you can either upload a new sketch. So it says here wait 5 seconds for upload, but you don't actually have to do that anymore. You can upload it at any point in time. So if I wanted to, I could then go back and, you know, even while I'm midway through running my sketch, I can upload a new sketch while it's doing its thing. So you see now it's the Arduino IDE tells the device to reset, and then it'll upload the code. So there is sort of still this reset and then 5-second upload thing, but the when you upload a new sketch, it forces the device to reset and do it anyway. So you don't have to worry about this so much yourself unless you're programming it without using USB. But it's neither here nor there. So yeah, it'll basically start executing your sketch until you push reset, which is this button in the corner here. So I push that and it'll just reboot the thing and just keep running the same thing. So, you know, depending on what your Arduino's going, sometimes you may want to reset it. So there's a little button here. On this one, it's in the middle there. Usually it's pretty much the only button on the board. We'll just turn it off and turn it on again. So yeah, an Arduino sketch, you have global variables, which are declared up top. So up here we have int LED 13. You have your setup, which is run at initialize, so you set your pin modes, whatever else. And then you have your loop, which runs indefinitely after setup, so right to the digital pins, delay, whatever else. And once you've hit the end of the loop, it just starts right back at the beginning of the loop again. So yeah, in LED pin is 13. All these sorts of things you might see in global variable. Set the pin to 13. Set up an analog sensor on analog pin 0. Set the current state of the pin to low, whatever. Set pin mode to LED pin output. So we've already seen this. Basically, set the output mode. This is one we haven't used so far. Let's have a quick look at this. So, as I mentioned, all Arduinos run work over USB on serial, and it's going to be right. Is it capital S? Yeah, there we go. So yeah, Arduinos run over serial. So communicate with the computer and everything using serial. So now if I run this, and this is something we didn't look at before, so the Arduino IDE also includes a serial monitor, so we can basically have a look what's coming in on the serial port, and in this case it says hello, and every time it runs loop it will print hello to the serial monitor. So, you know, it turns the LED on to high, waits a second, turns the LED on to low, waits a second, and then prints hello to the serial port. So you can see now we actually have this communication going from the Arduino back to the computer, which is kind of nice, because now you can imagine if you wire up buttons or, you know, sensors or whatever, now you can actually send that data from the Arduino back to the computer, and then have the computer do something with that information. So you can make your own game controller or wearable device or whatever that, you wear something on your hand with some flex sensors, and then you can read those values and do something with it on the computer. So you could, make a computer mouse or a game controller or whatever with the Arduino, read the buttons, and then send the results to the computer using serial begin and serial print and so on and so forth. We have in the loop, you might want to do things like digital write and digital read. So we haven't actually looked at reading stuff yet, but we will in a minute. And analog read and analog write. So we'll look at what those relate to in a minute. Delay, which we've seen, so you wait a certain number of milliseconds, and millis allows you to get the current time. So instead of waiting a certain amount of time, you could check to see if a certain amount of time has elapsed or see how long the program's been running. So if you want it to just sort of run for a certain amount of time without pausing, you can check millis and see what goes from there. So input and output, we'll just cover this and then we'll have a little break. So there's two different types of input and outputs on an Arduino board. There's digital I/O, so that's most of these pins down here are the digital I/O, so they either are a 1 or a 0 or a high or a low or 0 or 5 volts. And then down here we have 6 analog inputs. So analog traditionally means it's like an infinite number of values, so it can be fractions of numbers and everything else. In practice, obviously, with digital I/O or digital circuits and stuff like that, we can't do an infinite number of circuits because we just have to do what's known as quantization. So this is, your analog signal coming in here, and what we do is we use quantization to sort of say, okay, let's try and represent that with digital values. So this signal here might end up becoming this signal here after quantization, and this is where we have, basically 3 values. 3 positive values and 3 negative values. We say, okay, at time t, we can sort of map this part out to being, that's about a 2, sort of over here. I'd probably argue that it's actually a 1. But then you go, okay, at this time here it's 2, at this time here it looks like it's pretty close to being a 3, and so on and so forth. So you basically map it in from a, nice smooth analog curve to a discrete, blocky, digital curve, but you can sort of approximate this with this, and for most applications, as long as you've got enough values, this will look close enough to this that, certainly the electronics won't care. So yeah, the number of states we have, so in here we have, 6 states, or 7 I guess, 0, 1, 2, 3, and negative 1, 2, and 3, determine the resolution, so how accurate we can make our signal. So if we have 8-bit, we can do 256 different states. So we could, for a curve, we can measure it on 256 different things. If we have 16-bit, we can go 16,000. And if we have 32-bit, we can go to 4 million. So with Arduino, it's basically 8-bit. When we do analog out, we can do 8-bit values. So we can write out a value between 0 and 255. And for analog in, we can actually do 9-bit. So we can go 10-bit. Sorry, we can go 0 to 1024. So we can read a value. If we have something like, must be one in here somewhere. In one of these kits. Oh, there's a small one in here I saw. So we have something like this. So this is a potentiometer, and it's basically a variable resistor. So you'll see I can actually turn this, it's got a little arrow on the front, I can turn this round. And so this will be read as 0 by the device, and then as I start going around, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or whatever, till I get to about halfway, where it'll be at 512, and then when I get all the way to full around there, it'll be 1023. So I can actually measure how far I've rotated that round in steps of, one bit. As for pulse width modulation, I'll talk about that probably later, but pulse width modulation basically allows us to output, so we can do from 0 to 255. So what that means is we can output from 0 to 5 volts in 255 increments. So if I say, okay, output, 0, it'll output 0 volts. If I output 5, it'll output 5 volts. If I output, if I do 0, it'll do 0 volts. 255 will do 5 volts. And if I do, say, 128, it'll output 2.5 volts. So, and it's actually doing it by, there is a slide I do later on. I should probably move it to this part of the talk. But basically, it turns the power on and off really, really quickly. So if it's at 5 volts, or if it's at 255, it outputs 5 volts the whole time. If it's at 0, it outputs 0 volts the whole time. If I do 128, it outputs 5 volts half the time. Like in a second, it would output 5 volts for half a second and 0 volts for half a second, but like really, really quickly flashing between the two of them. And by doing that, we can do, make it look like we're doing sub-volts. So we'll just show a quick read analog, right. Oh, fade, that's the one I wanted. So here's an example here, which does, what pin are we looking at? LED on 9 now. Pin 9. And if I run this one, so this you'll see down here, instead of our digital write that we were doing before, where we just tell it a pin and a value, now we have analog write. There we go. So now if you look at the little yellow LED, it will get brighter and then it'll get dimmer. So it fades in and fades out. And that's basically doing this pulse width modulation. So it's if we put a digital multimeter over that, we'd see it going from 0 volts up to 5 volts and back to 0 volts. So it gets brighter and then it gets dimmer. And really, all we do, it's exactly like the digital write here, but instead, so we specify what LED, but instead of saying high or low, we pass in a number from 0 to 255. And in this one, it just basically increases the amount of brightness until it reaches 255. And then it decreases the amount of brightness until it reaches 0, and then it goes back and forth between the two of them. So we can fade our lights in and out by using this analog write value. So yeah, blink. We'll have a little break now while I set up these other circuits, and then we'll have a look at them afterwards. So yeah, I'm going to have a 5-minute break or whatever, to go to the bathroom, whatever, and I'll set up these circuits for digital read, serial, and analog read. And then, yeah, we'll have a look at them when we come back. Alright, so we will just get started again. I'll pick up where we left off anyway. So, we've had a look at blink. We do digital write, we turn an LED on, we wait a second, turn an LED off, easy. Look at fade. So fade used analog write, and it basically went from 0 up to 255, and then from 255 back to 0 to fade an LED in and out. So they're obviously output, and those are basically the two output functions of Arduino. You can either write a digital value, so 0 or 5 volts, or 1 or a 0, depending on how you want to look at it, or you can write an analog value, so 0 to 255 or 0 to 5 volts in increments. So that's output. And as far as input goes, we have digital read serial and analog read serial. So, we can write a value out to turn an LED on, turn a motor on, whatever else. And we can then read back a value in. So how this works in practice is we basically actually just check the voltage on a line. So you can imagine if we have our Arduino here, and we have some pins, and we have this, so this is an input pin. Basically, what we're just doing is measuring what that voltage is, or what the voltage on whatever line we connect it to is. So if, say, here's a line here, and we'll just say here's my 5 volts here, and if that's connected up to here, and then I connect my input in like that, this will read digital read will return 1. So 1 equals 5 volts. So it's basically reading where I'm connected to on this line, what is the voltage at that point compared to my 5 volts. So if it's 5 volts, it'll be 1. If this was instead connected, say down here, we have ground or 0 volts. And if that was connected in like that, our digital read would return a value of 0, which equals 0 volts. So it basically it's just a way of like looking at what power is running through that line and saying, is this 5 volts or is this 0 volts? And it returns that. So, you know, it might seem pretty trivial, but when we actually try and explain this example, it's a lot easier to draw it out. So if we go to the Arduino website and we have a look at our digital read serial, this example shows you how to monitor the state of a switch by establishing serial communication. Well, okay, we've looked at serial communication. We know we can do serial.begin to turn serial on, and then we just do serial.print to write. But what is actually more interesting for us at this moment is using digital read. So we build this circuit here, and we essentially have a switch in the middle, and we have a pin 2, which is going to be our sensing pin. So this will be that pin which comes out on our board to check what the voltage is. And then we have, 2 connections in here. So we have 5 volts going into one side and a resistor going to ground on the other side. So let's have a look at these switches first. So this is the switch that you guys get in the board. So typically when you see a switch, they're drawn like this in an electronics diagram. So this is an open switch, so we have power goes in this way, and then it goes up here, and if they're disconnected like that, then no power will come out, and then a closed switch looks like that, so power's going in here, crosses here, and goes out like that. So if it's open, no power can flow through. If it's closed, power can flow through. The ones in the Arduino are a little bit, can be a little bit confusing because they actually have 4 legs on them. And essentially what's happening, let me just double check to make sure I'm correct in this. Yeah. So we essentially have these are the 4 legs. Something like that. So the 2 of the legs on each side are connected to each other. So if we have a look at this one here, which way is it? I think it's across, isn't it? Oops. Yeah. So these 2 legs are always connected to each other, this one here and this one here. So it's actually like we have a wire running from that leg to that leg, and in fact inside the switch that's exactly what's happening. And then we have the same thing on the other side. So these 2 legs here are always connected to each other. So we have a wire running between the 2 of them. And when I push the button, so you can hear the button click, when I push the button, it basically connects all 4 of the legs together. So if it's open, these 2 are connected and these 2 are connected. If it's closed, all 4 are connected to each other. So it's basically like this. 2 legs are connected to each other, the other 2 legs are connected to each other, and when we flick that switch, everything's connected to everything else. So have you guys had much experience with multimeters? Some of you, yeah. So I'll just look at this quickly for how I was able to do that. So there's a multimeter, so it basically allows you to measure a bunch of stuff. We've got at least one of these in the lab. I think we might have a couple, but I'm not sure where the other one is. So it's got a bunch of features on it. So you can see we twist this little knob around to select what we want to do. So off is off, and turn it off when you're done with it, or the batteries will go flat. Then this first one, V, with some lines on it. It's very small, so maybe I'll write the symbols up on the board. We have V, like that. So that's for measuring DC voltage. So that's if you're ever wanting to measure voltage, that's the one you do. Then there has a V like that, which is analog voltage, which we're never going to be working with this in this class, so you might as well just ignore that one. Then we have the ohm symbol, which is resistance, which is actually what I was using and basically measures how much resistance there is between 2 objects. So for my switch, which I have placed somewhere, and I did 2 things. So yeah, if I can somehow prop this up so you guys can see it. If I try, so right now you see, I'm measuring voltage. If I do resistance, you see it says 0L, which means that basically there's an infinite amount of resistance, so there's no connection. Sorry, you've worked with a multimeter before anyway, so this you don't need to see this. yeah, so 0L basically shows there's infinite resistance. If I touch the two leads together, you'll see it goes down to 0, and this, it's a little bit confusing, but over here you can have mega ohms, kilo ohms, and ohms. So obviously the larger the number is, the more the resistance there is. So we start off at infinite. If I squeeze the two of them together in my hands, we've got 1.45, and if you look, that's mega ohms, so there's 1.45 ohms of resistance through my body. If I do them both on the same finger, that number drops down to 0.8. If we then run through this resistor here, come here, we'll see that that reads 322 ohms, and this is supposed to be a 330 ohm resistor, so it's close enough, it's within tolerance anyway. And somewhere I saw just before, where were they? Because I took one out. Oh, I'll just borrow this for a second. This one here is, so see there, that's 10, and then it says K ohm on the thing, so it's a little over 10 kilo ohm, and this is a 10 kilo ohm resistor, so that's good. Yeah, so you just got to look at the, make sure you check the number or the units which it uses, so whether it's mega ohms, kilo ohms, or ohms. But basically the way I use that to figure out the switch is if I connect two of these on opposite sides, come here, we see a value of, it's done its thing, hold on. Incredibly fiddly. There you go. So if I connect two of these on opposite sides, we see 0 ohms, more or less. So that means that these two legs here must be connected, and if I measure these ones here, it'll be the same. And then if I connect the side-by-side legs together, I'll do diagonal, it'll be a bit easier. You'll see that's actually reading the resistance through my body, but it's a huge number anyway. But then if I touch the two of those together and then push the button in the middle, it'll go down to 0 ohms. So when I touch the two legs across it, across the ones which are connected, we get 0 ohms. If I do them diagonally, so the ones which aren't connected, then it'll be as close to infinity, especially if I don't touch it with my hands and it's measuring the resistance through my body. And then when I push the button, it goes to 0 again. Anyway, that's how we figured out which legs were connected to what in the button. But let's have a little look at how the circuit works. So this is the schematic for it here. And basically we have D2, so this is our digital pin that we're going to use to check the voltage, goes out and it connects, and on one side it connects to the switch, which comes from 5 volts, so 5 volts goes into the switch, and if the switch is, well, yeah, into the switch, and then it goes across this line, and it goes into a resistor, and it goes to ground. So if the switch is open, there's going to be no voltage passing through here, and this is essentially going to be connected to ground. So if the switch is open, the switch here is open, then this is effectively connected to ground. If the switch is closed, then 5 volts is going to flow from here through the resistor and into ground. And we're going to look at this a bit later on, but basically the way, when we look at current or voltage flowing through a circuit, the voltage will be proportional to the amount of resistance. So because this is the largest source of resistance in the circuit, most of the voltage will drop across here. So on one side of this resistor will basically be 5 volts, on the other side will basically be 0 volts. And so if this is on this side, it's 5 volts here, so it'll be 5 volts here, so this will read 5 volts. Does that make sense? Yep. So if we look at it in practice, so this is the pin here, or the circuit here. Now you can see that, you know, the pin, this is actually over this side because I've tried to copy this circuit diagram here, where you see the digital write goes over to this side, but to be honest, we can just as easily actually pop that over there and everything will be fine. So let's then open up our digital read code. So if we have a look here, we define, we're going to, well, the button, digital pin 2 has a push button attached to it, so we're going to say number 2, serial begin 9600. So I didn't say before, but this basically is the speed that the serial port will operate at. So this is 9600 baud, which we're usually going to use. It means it can send 9600 bits, which is kind of slow, but most of the data you're sending from the Arduino won't be, you're not going to be sending huge amounts of data anyway, so usually that's fine. And then we're instead, like before we saw pin mode, and then we gave it a number output. Now we're saying it's input. We're going to read the value off this pin. We're not going to be sending data out of it. Then in our loop, we basically int button state equals digital read push button. So digital push button is pin 2. So on pin 2, we're going to read what the value is there, and then we're going to print that out to our serial thing and wait 1 millisecond and then run the loop again. So if we upload this to our sketch, or sorry, upload our sketch to the Arduino, and hopefully if I've plugged everything in the right way. So you'll see I'm not pushing the button down and it's reading 0, so the button's not pushed, and then when I push the button in, it goes to 1. So if the circuit's open, this is basically connected to ground. There's no voltage passing through, so it reads as 0 volts. When I push the button, voltage is passing through the switch, and it goes in. Then when it reads it, it's saying, okay, there's 5 volts at this point. So now we are able to physically interact with our computer by using 3 wires, a resistor, and a switch, which is, you know, really simple, but it's kind of neat that, you know, rather than just relying on people building their own devices, keyboards, and mice. If you think about it, if you had like 26 of these buttons, you could make your own keyboard now. Well, you'd probably want more than 26 because then you'd have no space or enter or numbers. But if you had enough of these buttons anyway, you could build your own keyboard, and obviously enough ports on the Arduino. But then you can actually do that. You just need to start scanning across the board, and it's way outside the scope of what we're trying to achieve in this course. So just forget I mentioned it. But you could do it anyway if you felt so inclined. It would probably be a very uncomfortable keyboard to use because those buttons are kind of a pain to push. So that's digital read serial. We're reading the amount of voltage at a specific point in a circuit. So we don't actually break the circuit to go into it. We just tap it out, and it's basically just like, you know, peeking into the circuit at that point and saying, what is the voltage here? So let's have a look at analog read. So that's digital. You know, we're looking at a 1 or a 0. Let's have a look at analog read. So the circuit for this one is even simpler. Get rid of that. With these ones, they don't plug into the breadboard that well. That's why I was holding it like that. So, you know, I was holding it to make sure that the pins stay in. You can do what somebody's done with this one here and basically just solder like a little header onto the bottom if you want. I mean, feel free to do whatever you want to the kits. Try not to completely destroy them, but if you want to solder bits and pieces on, go for your life. Right, so let's plug this in. And what we want to do now is we want to put voltage plus into one side of this. So, So these potentiometers or variable resistors have 3 legs. So one is, or the leg on the leftmost side or the rightmost side, it doesn't actually matter because they work in either directions, will be the minimum voltage, so usually ground. The pin on the other side will be your maximum voltage, so 5 volts or whatever, and then the pin in the middle is the sense pin, so that's the pin you're going to connect to your analog read thing. And then when you turn it all the way to one way, it'll connect it to one side. When you turn it all the way the other way, it'll connect it to the other side. And yeah, so if you turn it all, like say if I turn it all the way that way and it's reading 0 volts and I really want it to read 5 volts, all I have to do is pull out the ground and 5 volt pin or things and connect them around the other way, and it'll work opposite. But yeah, plug that in there. And then we'll connect 5 volts to, whoops, I just short-circuited it, so it's just packed to SAD. 5 volts to one, and ground to the other, and we'll put the sense pin in the middle. And let's jump into file examples, read analog read serial. So this one is pretty much the same as the other one if you look. Actually this needs to be in an analog port now. So as I said earlier, these are digital pins, they only do 1 and 0. These are analog pins, so they do the other one. So if you're doing analog reading, you can actually do pulse width modulation off most of these. So the ones which have the squiggly line on it, you sort of see PWM squiggly line, those are ones you can do analog write out of. The analog ones down the bottom are actually only for analog reading. You can use the digital ones for reading or writing digital and writing analog. These ones are just for reading analog, just to confuse matters a little bit, but yeah. So hopefully if I upload that now. And so yeah, this is reading 1023, so if you remember it, it's a 10-bit thing, so I can go from 0 to 1024, and as I turn this around, once I figure which direction it goes, it will gradually decrease until we hit 0 volts. So yeah, now we can basically measure how far around this has been turned. So if I put it roughly in the middle, it should be 512, somewhere around there, so in the middle. So yeah, that's how easy it is to do analog reading. You just call analog read and what pin you want to read from, so A0. So you'll notice with the digital pins, they just have a number. With the analog pins, they have an A and then the number. And there's only 6 analog in things, so yeah. You not that often to read it. But yeah, so I mean, this is obviously quite simple with a potentiometer, but you'll see things like accelerometers and stuff might have analog values as well, so we could plug an accelerometer in here and then measure its orientation in space and that sort of stuff as well. One of our master's students from, was it last year, or I can't remember if it was the start of last year or the end of the first semester of last year or the second semester of the year before that, she did a project with Science Alive with a body scanner. I don't know if you guys have seen it, I guess you have, because I sent you the paper, but basically she did a mannequin body scanner and it had the equivalent of a potentiometer in it, and it was like a sort of CAT scan machine. It had a mannequin in it, and then you slide it from side to side and it had a little screen on it, and you could see like an X-ray, augmented reality X-ray over it, and she basically used a potentiometer that measured how far you'd slid the thing along so that it would update the screen as it went, and you know, with this many lines of code you can get the position of the screen. And then you just read the serial value out and pass that into your program. So yeah, some basic examples there, but you know, you can hopefully sort of start getting an appreciation for the sort of things which are possible with just writing either out a 0 or a 5 or a 0 to 5 in 255 increments, and then reading either a 1 or a 0 from a digital push button or like an analog value from that. Yeah. So does anyone have any questions about any of that? Nope. All right, so we'll make a start on the next set of slides. Oh, also, the last Arduino arrived this morning, so you guys can go for your life, take one home. The only thing is, they were all supposed to, well, they did all originally come with these SparkFun books. Well, which have basically, you know, a bunch of different things like how to make music and shift registers, and it's basically just a project book. You guys have all got the prototyping interactivity textbooks, or you have access to them anyway. They've got a bunch of Arduino examples in there as well. There is these books, we've got one here, and this one will have another one in it as well. I'm pretty sure you can get a PDF of it online, and the books will be in the lab somewhere. I'm not 100% sure where, but yeah, you might just, if you can't find a book, I'll have a look to see if I can find the PDF of it, and if I can, I'll link to it on Learn. Otherwise, you know, you might just have to share the books if you want to have a look through. It's got some cool projects in there, like how to do various bits and pieces, and it, you know, these are all the, like it's specifically designed for these kits, so it uses the hardware which comes with them, like shift registers and piezo speakers, push buttons, photoresistors, all sorts of stuff. So yeah, there's only 2 of them between the 4 of you until I can track down the other ones or track down a PDF, but otherwise all the bits and pieces should be there for them. No, for the SparkFun manual. Programming Interactivity also has a bunch of Arduino examples in there as well. So I mean, you can use either. There's probably a fair amount of overlap. It's just, if you guys are really keen to try out all the demos you can do with the SparkFun Inventors kit, yeah. But that's up to you guys how far you want to play with them until you get bored. All right, so we'll just get a little bit into some electronics theory now. That's probably about all that there is really to say about Arduino. You program it, and then you can push some voltage out of it, or you can read some voltage into it. That's what it does. What gets interesting is when you actually start plugging into some electronics and doing some interesting stuff with it. So we'll start with a bit of electronic theory. Some of this is incredibly basic, but some people have never done electronics, so they have no idea. But yeah, electrical energy is one form of energy. Obviously, there's other types. There's light energy, magnetic energy, heat, chemical, pressure, etc., etc. And the law of conservation of energy states that energy can neither be created nor destroyed. It can change forms and flow from one place to another. So you can turn electrical energy into light energy like we did with the LEDs. We didn't do anything with magnetism, but heat, if you get a little bar thing, or bar heater, you can plug it into your Arduino and heat it up. So on and so forth. So with electric charge, it depends on an imbalance of protons and electrons. So obviously inside an atom, you have protons, neutrons, and electrons. When we take some electrons off an atom, it becomes positively charged. When we add it back up, it's neutral, but the electrons carry the negative charge. So yeah, this results in either a net positive charge or a net negative charge. Like charges repel, opposites charges attract. So if you have 2 positives, they'll push away from each other. 2 negatives will push away from each other, but a positive and negative will attract each other. So electric circuits. A circuit is a closed loop through which charges can continuously move. So we have a circuit here with a battery and a light, and one side of the battery will be predominantly negatively charged and the other will be predominantly positively charged. So all these negative electrons are going to push against each other and go around to try and meet up with our positive electrons our positive nuclei at the other end. So these electrons are going to pass around to try and balance it out. So instead of it being negative here and positive here, it wants a net overall neutral thing. So a circuit is derived from the base word of circle, which describes how the electrons move. So traditionally, way back when, they sort of thought that it was the positive charges which flowed. We now know that it's actually electrons that pass through the wire. So the electricity is actually, the charges are technically moving from the negative to the positive. But you can think of it either way around, really. It doesn't make a difference. This is how it actually moves. But as long as you know things are going from one direction to the other, and you know which way to put your polar things like LEDs and stuff in the circuit, everything will be just fine. So you have to have a closed circuit, so this has to be a continuous connection because electrons can't jump gaps unless you're talking about ridiculously large voltages where you start getting huge big arcs and stuff, like if you do arc welding, but we're not doing that. So there must be an energy supply capable of doing work on charge to move it from a low potential energy to a high potential energy. So you end up with a voltage, so you have a high potential at one side, so 5 volts at one side, low potential at the other side, which is ground, and it'll try and get from the 5 to the ground. You can think of it like a waterfall sort of example, so you have, gravity is your potential there, so you have all the water at the top of a waterfall has high potential energy, and then it falls off the side of the waterfall to get to a lower thing at the bottom of the waterfall. Same thing. Must be a closed loop connecting them. Yep. So you have high potential energy. So this is sort of now the other way around, high potential energy here, and it's going to the low potential energy, but it doesn't really make a difference. So a circuit is a set of electrical components connected so they provide one or more complete paths for the movement of charge. So it doesn't have to be a single thing. So we could quite easily have a circuit which, so if we have our battery, use the correct symbol. We have our battery here, and it goes into an LED here. we can also have another LED like that, so it doesn't have to follow the same path. And we'll look at the difference between what's known as parallel and series circuits. But you can string this along like that, or you can have multiple ones in the same path, and so on and so forth. So yeah, one or more complete paths, so it has to connect all the way around, otherwise nothing will happen. And then you have what's known as a load, so a component or a group of components that dissipates the energy, so they convert the energy from electrical energy into heat, to light, to whatever else. And a simple circuit consists of a source of potential difference, so a battery, the USB provides power, or you plug it into a power source, and a load, so something which is actually doing something with the energy. So we have a closed circuit, which is where the whole thing's connected, potential difference exists and electrons flow. An open circuit, where you have a break in the circuit and nothing happens. And a short circuit, which I accidentally did with that Arduino before when I touched the 5-volt wire to the ground wire, and it actually caused the Arduino to reboot, which is not something you want to do. So try and avoid doing that if possible. Probably, unlike me, you should unplug your Arduinos when you're wiring it up and then plug it back in when you're finished. The bad thing about short circuits is basically, if you have something like this, you have your battery, and then it's connected with no load on it, it basically makes it incredibly easy for the electrons to get to here, so an absolute ton of them will move through, and this wire will heat up very, very quickly. And I'm restoring a scooter at home at the moment, and I accidentally earthed one of the, as I was screwing in a screw, I accidentally caught the voltage wire and earthed it against the chassis, and then the wire caught on fire, which wasn't awesome. But yeah, these are the sort of, with the sort of voltages we're talking about here, you're probably not going to get too much, but when you start dealing with things like, car batteries or scooter batteries, you're talking about things actually catching on fire. They're going to get so hot. So then I had to solder a new wire on. So different types of circuits. We have series circuits, where you have basically one single connection going from one end to the other. So objects are in series if basically one end connects to the end of the other one, so a single conducting path without junctions. And then we have a parallel circuit where there's two or more components connected across a common point or junction. So here we have, in this one, obviously the power has to flow through all three lights in one after the other. Here it can flow through this one or this one or this one at the same time. Current, so just some definitions of what various things are, because they can be quite confusing. So current is the flow of electrons or charge within a circuit. So we're basically looking at measuring the number of, we actually don't do a single electron, but we talk about a group of electrons, how many are moving through the circuit in an amount of time. So the word current is measured in formulas using the letter I, because it comes from an old Greek word, which I can't remember. And it's measured in amperes or amps. So, you have 1 amp of current or whatever else. The symbol for amps is A, and current moves away from a negative charge towards a positive charge. So, back in the old days, they thought positive went to negative, but it's actually negative which goes to positive, but it doesn't really matter in the long run. All you need to know is that, it's going from one place to another place. So an ampere is the amount of electrons measured in coulombs that flow past a point in a circuit in 1 second. So we're counting not individual electrons, obviously we're counting groups of electrons, but we're counting actual electrons as in the parts which orbit a nucleus. 1 coulomb, which is 1 amp. A coulomb per second is 1 amp, and a coulomb is comprised of million, billion, trillion, 6.28 million trillion electrons, so quite a few. And the word coulomb is represented in formulas using the letter Q. So current is Q divided by T, and measured using seconds. So 1 coulomb, so 6.28 million trillion electrons moving through a piece of wire in 1 second is 1 amp. Then we have voltage. So voltage is the electric potential per charge in a circuit. It's represented in formulas using either E or V, more commonly V. Voltage is measured in volts. The symbol for volts is V. So, each coulomb can have a certain amount of voltage. I sometimes, in past, have used, to varying extents of success, the analogy of, if you think of like current Well, if you think of like electric charge as being like a coal train or something, then current would be the amount of, like you have a train, and current is the amount of carriages that it holds. So, you know, you have 6.28 million trillion electrons, you have 6.28 million trillion carriages, and then the voltage is effectively how much coal is in each carriage. So each coulomb can be carrying a certain amount of voltage in it, a certain amount of electric potential. So 5 volts means that each coulomb contains 5 volts of electric potential within it. And then sort of the final thing, well, one of the final things anyway, to sort of tie it all up, is the idea of resistance. So resistance is the equivalent of internal friction. So using the coal train analogy, if you have a load, so a light bulb, a motor, whatever else, that's kind of like something which is taking coal out of each of the carriages and burning it. So, you know, you might have, I don't know, a mill or something, and the train passes through, and the mill takes some coal and burns it. And that's the equivalent of the resistance. So it's the amount of coal which needs to be burnt before it passes through. It's measured in ohms and represented in formulas as R. And it's related to voltage across an object and current through an object using the voltage V equals IR. So the voltage which is used by a certain load, so if we have, you know, a light bulb, will depend on the current divided by the resistance. So if say we had that 330 ohm resistor before, well, actually we'll do it the other way. We'll do 3. So we had one of these resistors down, this one here is 330 ohms. So we have our resistance equals 330 ohms. Then we have our voltage is equal to 5 volts. So we know there's 5 volts coming out of the Arduino and then going to 0. Then we can say V equals IR. And then we can basically jig that to I equals V divided by R, and we can use that to figure out what the current will be passing through that resistor, because the voltage is 5 and the resistance is 330, so we can figure out what our current should be when it's passing through it. So how many coulombs, how many coal trains will be able to pass through that resistor per second. Yeah. So there's various classes of objects based on resistance. So we have what are known as conductors, so like wires, which are very low resistance. They allow electrons to flow through them nice and easily. We have insulators, which have very high or infinite resistance. So, you know, we looked before, when I held the two ends of it, I had a resistance of some like 300 mega ohms or something. So I am quite a good insulator. Electricity can flow through me. However, we'd need either a very high current or a very high voltage in order to do so, which is why I can grab either end of a 9-volt battery and be fine. But if I stick a fork in the electrical socket and grab onto that, I'm probably going to catch on fire because they have a very high current and quite a high voltage. So, you know, all these things sort of trade off each other. People always say, oh, you know, some people say, you know, it's not voltage which kills you, it's current. In reality, it's a mixture of the two. So if you have a very high, it only takes like a very small amount of current to actually stop your heart. So if you have a huge amount of voltage and a low amount of current, it'll still be enough to kill you, and vice versa. So yeah, I'd highly recommend not grabbing onto things until you've measured, you know, what voltage and current you have. So yeah, conductors like wires, low resistance, insulators like me or the desk or anything which doesn't conduct electricity, very high resistance. Then you have semiconductors, which are pretty much everything which is interesting. So they will do stuff, they're somewhere in between conductors and insulators, and depending on how they're constructed, they may have special properties. So, you know, they might only allow current to flow one way through them, like a diode or an LED or something. You know, there's lots of various interesting things. Transistors, for example, only allow current to flow through them when they have a little bit of current going into them already. We'll look at all these things later on. And then you have superconductors, which we're definitely not going to be looking at in this course. But they basically have zero resistance at specific temperatures, which means you can do really cool stuff with them, like magnetic levitation and stuff like that. So I'm just going to show you a video of this because I know this is quite boring. But yeah, I don't want to watch a TED talk actually. Stop. Back. But yeah, so I'll just try and spice it up a little bit with, these are the sort of things you can do with superconductors because they're really cool. Assuming this is going to work. So this is a superconducting material, and it's basically magnetically levitating according to a track due to eddy currents and stuff floating through it. But it's kind of cool. Like, these are just ordinary well, they're probably rare earth magnets, so extremely strong. And then you have your superconductive material that when you cool it down, so you'll see on those zero resistance at specific temperatures. So you cool it down with liquid nitrogen to be extremely cold, and then it floats around attached to the thing like it's actually levitating. You can see it's not actually touching it, it's floating like half a centimeter above it, and so it has no real resistance or anything like that, but they're like super cool. They just float, and you can do all sorts of stuff like, they'll stay attached stuff. But yeah, I digress. It's just something interesting to have a look at because I think it's really cool anyway. So those are the sort of different classes of resistive objects we're going to look at. Conductors, which are wires; insulators, which is everything else; semiconductors, which is everything interesting; and superconductors, which is super interesting, but unfortunately we don't have any. So measuring voltage, current, and resistance. So here is another digital multimeter like the one we saw before. This one's a little bit different from the one we have because here you actually have to specify, when you're doing things like measuring voltage, measuring amperage, you need to sort of say, here is the maximum cutoff. So here, if you're measuring, so DCV is DC volts. So, if we're using a 9-volt battery, we'll say, okay, well, it's never going to go above 20 volts. So we're probably fairly safe here. If, even a car battery is only 12 volts. If we were doing something with like a transformer, which transforms it up to 120 volts or whatever, would want to be up here. If you plug a 9-volt battery in and then try and measure it on 2000 millivolts, you'll probably blow the fuse in the digital multimeter, and then you won't be very popular. So you're always better to start at a higher number, and it'll just say 0, and then slowly crank it down until you see a number which seems reasonable. And with resistance, it's not such a big problem. It's mainly with definitely with like current, so amperage and voltage. But yeah, so multimeters can measure voltage, current, and resistance. So, sorry, I'll just turn that back on. So they can measure, we have voltage here, so the voltage with the straight lines on it is DC. The resistance is the little ohm symbol, and down in the end we have current, so we have UA, so microamps, milliamps, and amps. So again, before you connect it into your circuit, wind it all the way around to A, then connect it in, and if you don't see a value, scroll it back to MA, and then if you still don't see a value, scroll it back to microamps. Don't start at microamps and then work your way up because you'll blow the fuse, and then you'll have to replace it. Otherwise, you're going to upset someone later on. And this is... If you take nothing out of this lesson, remember this. Voltage is measured as the energy difference across an object. So if we have a circuit here, here's our battery, here's our light bulb, you basically just connect it across the circuit. So don't touch the circuit, just say, okay, I want to measure what the voltage difference is across this light bulb. So let's do an example here. That up to there and around, and then hook this one up to 5 volts. Right, so say I want to measure the voltage across this LED. I will flick it round to volts, and I will put one end on one leg of the LED, the other on, prop this up so you guys can see it. One lead on one leg of the LED, the other lead on the other lead on the other leg of the LED, and I can't actually read what that says. So that's about almost 2 volts running through the LED, and then if we do the rest of that 5 volts, then must be on there. So that should be Where are we? Just if I actually touch it. So about 3 volts. So we had about 2 volts running over the LED. Then we have about 3 volts running over the resistor, which adds up to 5 volts plus or minus. So that's all good. What you don't want to do is unplug that wire, touch that to there, and touch that to the leg of the LED, or you will blow the fuse. However, if I want to measure the current through a system, I scroll around to amperage, and then that's exactly what I will do. So I will hook one end up to there, one end up to there, and in this case, amps is too high, so I'll scroll down to milliamps, and put that there so you guys can see. It is 9 milliamps running through this circuit, so not a huge amount. If I'm measuring amps, what I do not want to do is measure one leg of the LED and then measure the other, or you will blow the circuit. So yeah, kind of a bit frustrating. One way you have to break the circuit and put the thing in, otherwise you will blow the fuse. The other way you have to break the circuit and put it in, or you blow the fuse. So it's very important you remember which way it is round. If you're measuring the voltage, you're measuring the voltage over a component. If you're measuring the current, you're measuring the current through the circuit. So if it's over it, you leave everything as it is and just measure it. If it's through, you actually have to break the connection and run the power through the multimeter. Otherwise, you're most likely to blow a fuse. Depending on how smart the multimeter is, it may just switch itself off if you're lucky. And if you want to, so that's how you measure voltage and current. If you want to measure resistance, what we do is we scroll around to resistance, and then we go, okay, let's measure the resistance of this LED. This resistor, sorry, you pull it out, and then you measure it separate from the circuit. So this one is 328 ohms, so just shy of 330, which is what we would hope for a 330 ohm resistor. Can't get delete. There we go. So yeah, burn this into your memory, because we only have one multimeter that I can find, and if you're blowing the fuse every 5 minutes, you're going to upset a lot of people. So yeah, voltage across, current through, measure resistance separate. We've got a few more minutes. So power is something different from voltage and current and resistance again. So power is the amount of energy used when a circuit is closed. Power is calculated for time periods, watts per second, watts per hour. So this is what you're paying for from your electric company. You're not actually paying for the amount of voltage they provide, because in New Zealand they should be 230 or 240 volts. You're not paying for the amount of current. You're actually paying for how much power you're using. So word power is represented in formulas using letter P. It's measured in watts, which is the amount of energy used. And components in a circuit either transfer, store, or transform power. So conductors transfer power, wires allow power to travel through them. Cells and capacitors store power, so when you charge a battery, you're storing power. We'll look at capacitors a bit later on. And speakers, LEDs, motors transform power, so they're transforming it from electrical power to light power, whatever else. And that's actually probably a good place to leave it for today. Does anyone have any questions? No? So next week we'll be looking at actual electrical components, like what various things do and stuff like that. In the meantime though, I guess you guys have got your assignment to work on. So we were originally going to do like a combination of processing and Arduino, but I think we'll do processing in this part, and then the next assignment will be Arduino based stuff. So yeah, have a start of that, and otherwise you can collect your Arduinos, take them home, play with them, make sure you know what you're doing,